Hey everyone, so this is the next section of the dynamics unit, which we're going to talk about with friction. Now, we've kind of already discussed friction in some of the problems, but now we're going to go into a little bit more of a deep dive. So, what is friction? As we've already seen, friction is a force that opposes motion. So, anytime we have an object moving, there's always a force of friction acting in the opposite direction. Now, one thing that I want to point out is while that is true about the object moving, there's one thing to point out is that motion in this case doesn't just mean movement, it also means the at rest and the attempt to move. So for example, if you have an object that's at rest and you start to push on it, you are attempting to change its motion. Therefore, friction will act to oppose that motion, oppose the attempt to push for it to move forward. So a lot of times what you're going to say is that friction opposes the direction it's moving in or the direction that it wants to move in. So, for example, if I'm pushing a block to the right, or there's a block at rest and I attempt to push it to the right, but it remains there at rest, it's because there's a frictional force acting to the left in the opposite direction. All right. Friction arises because of the bumpy surfaces of the objects, and those bumpy surfaces rub against each other, and that ends up actually creating the friction because these bumps kind of latch onto each other, and that's all you really need to know about friction. There's two different types of friction. There is the static friction. Now, the static friction is the frictional force needed to keep an object at rest. So anytime an object is at rest, it's going to experience static friction, the force holding it in place while it is remaining at rest. On the flip side, we have kinetic friction. That's the other one. This is the force of friction that an object that's moving, sliding in motion experiences. And this is what kind of causes the object to slow down and come to a stop. Now, it's very important that I point out that kinetic friction is strictly when the object is sliding. A good example of this is a wheel. What type of friction does a wheel experience? Well, since the wheel isn't sliding on the road, it is actually experiencing static friction. Even though the wheel itself is moving, the part that's touching the surface actually isn't. It's staying still, it's staying in contact with that specific point of the road as the wheel kind of rotates around it. Another example is if you have an object, like let's say you have a dresser on the bed of a truck and the truck starts to move, technically the dresser is moving relative to the earth, but relative to the truck, it is stationary. So that dresser will be experiencing static friction. So it's important to keep in mind that kinetic friction is referring to the objects sliding, the two surfaces sliding against each other. Now, there is a frictional force equation that you get to use. The equation is FF is less than or equal to mu Fn. Now, two things that I want to point out. First, you might notice these two absolute value bars. I mentioned this before in class that the absolute value bars are meant to show that this is only relating the values of friction to the value of mu Fn. This has no indication on direction. I said this before that a lot of times in equations, when you have vectors, you can actually determine direction based off of the equation, depending on which vectors are where. In the simplest cases that we have, F net equals ma shows that acceleration and force are always pointing in the same direction. There's another equation that we'll see later on this unit called fx equals negative kx, and that shows that x and fx are in opposite directions because of the negative sign. Here, these absolute value bars are strictly saying while the values might be equal, the direction has no indication. Another thing to point out is that you have this less than or equal sign. Now, I'm going to point out what that refers to, but it turns out that the frictional force can sometimes be less than this value. And the mu term is the coefficient is refers to the coefficient of friction, which is for the most part a reference of how rough two surfaces are, how sticky they can be, if you will. So if an object has a very high coefficient of friction, that means that it's really rough to slide against. If it's really low, then that means they're very smooth. One thing to point out is that the mu refers to two surfaces, not just one. So it's the coefficient of friction between skates on ice or something. and that would be those two objects. That would have a slightly different coefficient than wood on ice. So yeah, I kind of mentioned this. High coefficient means that it's harder to rub and it's rough. Low coefficient means it's easier to rub and the surfaces are smooth. There are no units for mu, so if you look back to the equation, it's FF is less than or equal to mu FN. FF and FN are both measured in newtons, so mu is nothing. All right. Now, because we have two different types of frictional forces, that means that we have two different types of coefficients of frictions. So obviously the coefficient of static friction is used for when the object's at rest, and then we also have the coefficient of kinetic friction for the objects in motion. Now there is one thing to point out about the static coefficient. This is used to determine the maximum static force that can be applied, that the object can apply, and the maximum amount of force that you can apply before the object moves. What do I mean about that? Well, let's say you use the static coefficient on an object that's at rest, and you find that the static force is 40 newtons. Okay, but technically, if you apply 30 newtons of force to the object will still remain at rest. It would not make sense for there to be more frictional force than the force you're applying. So this is where Newton's laws come into play. When you have an object that is at rest, we know for certain that because of Newton's laws, that the forces acting on that object have to be balanced. That if you're applying 30 newtons of force to in one direction, there has to be another force pushing 30 newtons in the other direction in order to keep it in equilibrium and keep it balanced. In this case, that's the static force. So this is actually the reason why the equation is written as less than or equal to as a reference to this, that technically the static force can be any number up to mu Fn. So if the max static force is 40 newtons, then if I apply any force between 0 and 40, the static friction will be equal to that because the object will be remaining at rest. And once I apply 40 newtons, well, then it's still going to be 40. But once I apply 41, or just a hair above 40, all of a sudden the object will no longer be static because the static force cannot hold on to it, and it will start to move, and the kinetic friction will come into play. So that's the thing to keep in mind. Static friction can get a little bit tricky, but it's easy as long as you keep in mind the core concept that Newton's laws must always hold true. Everything that we talk about is based off of the validity of Newton's three laws. Now, one thing to keep in mind is that the problems usually give you the coefficients. Any sort of AP problem, they'll give you those coefficients, or sometimes they might ask you to find the coefficients, but they'll give you enough information for that. However, the Regents reference table technically has some coefficients. So if we're ever doing Regents problems, and if I forget to give you the reference table, feel free to look it up or ask. I have plenty of copies that you can grab. But the regions problems will just kind of assume you know it because of the reference table. But you don't have to memorize any coefficients. The only thing you really need to know or memorize is that the static coefficient is always greater than the kinetic coefficient. And this basically means that it's harder for an object to start its motion than it is to keep an object moving. If you've ever tried to move a dresser at home, you've probably experienced this before, that it requires a whole bunch of force to start the motion, but once you have it, it's a lot easier to kind of keep it in place. And the reason being is because the static coefficient for objects is generally higher than the kinetic coefficient. All right, so here's a problem. Work on this. We'll go over in a second. All right, we're just going to go through all these problems. First off, the creates weight. A big issue that people have with this is that they always confuse mass with weight. Do not confuse mass with weight. Weight is in newtons, so we have to do FF equals, oh yeah, you should draw an FBD. So the FBD should look like this. Keep in mind that even though the FBD tends to have 4 forces, it doesn't always have to be 4 forces. There could be more, there could be less. All right, so the crate's weight is Fg equals mg. Plug in the numbers, and we get 200 newtons. The force of the floor acting on the crate is just another way of saying the normal force. Because of the fact that in the vertical direction it's going to be in equilibrium, the forces will be balanced, so that normal force will be equal to Fg. Now remember, we have to show this, so we show it by writing some of the force in the y equals 0. equals Fn minus Fg because we have one force going up and one force going down. So Fn equals Fg, and we get that Fn equals 200. Now, to find the maximum force that we apply before the crate moves, that's just another way of saying what's the maximum static friction that the object can experience. So we use the static coefficient into our equation. So Ff equals less than or equal to mu Fn. Plug in the numbers, and we get 84. So again, because the forces in the x direction are going to be balanced, because the object is at rest, then I know that the applied force will also be a max of 84. And then what's the net force for this acceleration when 100 newtons is being applied? Well, now that I know that the maximum force that can be applied is 84, the 100 newtons tells me that the object is moving. You can't assume that the object is moving just because they say, oh, what's the net force and acceleration? That's a trick. So you always have to make sure that you determine what the static friction is first to see if the force that you're applying is going to be greater than that static. So this 100 is greater than the static, so I can use the kinetic friction. I get that the kinetic frictional force is 60 newtons. Then I do my net force equation where I subtract these two forces. I get that the net force in the x direction is going to be 40 newtons. And then I can plug this into the F net equals ma equation to get that the acceleration will be 2 meters per second squared, both in the direction of the applied force. All right. So we'll go over this in class. So here's the next question. We'll go over in a second. All right. So we have a steel container placed on the back of a steel truck bed, and we want to know what the maximum acceleration of the truck is before the container falls off. So this seems like it's going to be a little bit more complex, but it actually isn't too much. So first, they want the max acceleration. Well, first, that's a clear indicator that I need to find the net force or a force acting on the object, because I can find acceleration with the whole F net equals ma equation. In this case, there's really only one force acting horizontally onto the object, and that is the frictional force. Because the object well, there's two things. One, the fact that they say the phrase maximum acceleration, and the fact that the object is going to fall off the back of the steel bed means that the force acting on this is static friction, not kinetic. So, because we're looking for before it falls off, so before it begins sliding out the back of the steel truck bed. So we're going to look on our reference table. This is from the Regents reference table. Go for static steel on steel. And when we plug it into mu-fn, we end up getting, so I took this, I set the mu-fn, since fn is going to be equal to fg, which it almost always is half the time, I could just simplify this as mu-s mg. And then again, this is going to be equal to the net force, so equals to ma. So the masses actually drop out. Turns out that 40 kilograms is not necessary. We solve for the acceleration, and we get 7.4 meters per second squared. Of course, you could take this in smaller steps, but I'm just trying to show the quickest, simplest way of going through it. All right, and that's about it. We have a few more practice questions, but we're going to do that in class. If you have any questions, feel free to let me know. Otherwise, good luck. Have a great day.